Today our topic is coastal protection. Previously, we have looked at the Morrison equation and the derivation of the force per incremental length. Right now, we are going to apply the equation to a vertical pile and integrate in the vertical direction from z equals to eta at the water surface down to z equals to negative d at the seabed or mud line, where d is the water depth. We have the first term here, which is the drag force, and the second term here, which is the inertial force. For the drag force, it depends on velocity u, which is function of z, and for the inertial force, it depends on acceleration, partial u or partial t, which is dependent on z. So when we integrate this part of the expression doesn't change. So we can see it over here, but when we integrate u, we are going to see the additional expression over here, including a phase term cos squared. Likewise, when we integrate the inertial force term here, this part of the expression didn't change, and when we integrate partial u or partial t with respect to z, we get these additional expressions, including a phase term sine. Now the phase angle theta is equals to kx minus sigma t, where k is the wave number and sigma is the frequency number. Assuming that the pile location is at x equals to 0, basically the pile equation is a fixed position. So we drop the term kx. That's why for the phase term we are only left with negative sigma t, meaning that the force will still be changing as a function of time due to the cyclic or orbital wave motion. Now we also want to take note that the cos squared term here actually means we have cos multiplied by the magnitude of cos. So the sign of the expression will be maintained by this part, okay, whereas the other part only takes the magnitude, so that cos squared still will have a sign. The sign is important so that we can distinguish whether the drag force is positive or is negative at any particular time. So if we look at the entire expression, we notice that right now, after integration, the total force over the pile from the bed to the surface of the water is given by this very long expression, okay. But basically it depends on the drag coefficient and the inertial coefficient. As before, we have the term rho g. It depends on the diameter, the wave height, and as before is the ratio of the group celerity to the individual wave celerity. And we have a tangent hyperbole kd here. So pretty much it is more or less still depending on the same thing, except of course you notice that the wave height comes into the equation because velocity and acceleration basically depends on the wave height. Using the same approach, we can also determine the moment on a vertical pile. We multiply the force per elemental length with d plus z, whereby d plus z describe the position measured from the seabed to a point given by the z coordinates, and then integrate this expression with respect to z from the surface of the water to the mud line. The result of that gives us the expression for the moment, whereby the first line here is the moment due to drag, and the second line here is the moment due to inertia. We can see the familiar expression over here, which is the same expression we see in the previous slide, where we integrate to obtain the total force on the vertical pile, and this is also the same cosine phase term in the previous slide. Likewise, for the inertial part, we also see this familiar expression in the previous slide on the total force on the vertical pile, as well as the phase term in terms of sine function. So essentially, the integration of this expression gives us the additional expression over here for moment due to drag, and the additional expression over here for the moment due to inertia. For both the force and moment on the vertical pile, the peak value will occur at some point depending on the wave and the pile characteristic, as we will see in the example. In this example, we have a vertical cylindrical pile having a diameter of 0.3 meter installed in a water that is 8 meter deep. For an incident wave having a height of 2 meter and a period of 7 seconds, determine the horizontal force on the pile and the moment around the mud line when the pile is situated at the halfway point between the crest and the still waterline of the passing wave. Remember that here the pile is in a fixed position and the wave is passing by. So we are going to borrow the same plot that we have seen previously. The horizontal axis is still the phase angle, but since the pile position is already fixed, it's given by, say, x equals to 0. So we drop the kx term and we are left with only the negative sigma t term. So for this fixed pile in this location, the wave profile, the drag force and the inertial force right now changes with time only. It no longer changes with space. And we want to look at this specific time when the pile is between the crest and the still waterline. It's halfway between these 2 points. So in the phase angle axis, if this is 0, this is pi over 2, so this location right now is given by a phase angle of pi over 4. In order to solve this problem, we know that we're going to need to apply the equations derived for the total force and total moment on a vertical pile. In order to do that, first we're going to determine the values of some of these variables. We proceed by first using the wave period t in order to derive the deep water wavelength. And after that, we consider the water depth of 8 meter. We use trial and error method to determine the wavelength in this particular position, which gives us 55.2 meter. So with that, we are able to determine the wave number 2 pi over L. And also we are able to check the d over L, whereby d is the pile size. Compared to the wavelength, we get 0.005, which is smaller than 0.05, which means that Morrison equation is valid for this case. And we can also check that in this case, the relative depth d over L shows that this location we have transitional wave. We use the expression for the wave particle velocity u and found out that u equals to 1.24 meter per second, and we use this value over here to determine the Reynolds number given by u times d over nu. Nu is the kinematic viscosity, standard kinematic viscosity value for water. So we obtain the Reynolds number, and based on the Reynolds number, we are then able to calculate and choose the appropriate value of the drag and inertial coefficient to be used. The next thing we need is n, which when calculated gives us the value of 0.8. This confirms again that we are in transitional water, because we recall that in deep water n equals to 0.5 and in shallow water n equals to 1. So now we're ready to apply the equation for the total force on the vertical pile. We can substitute in all the values that we already found, and with that we should be able to calculate the drag force given by 425 Newton and the inertial force given by 637 Newton. Here we notice that the inertial force is larger than the drag force, and the total is 1062 Newton. Take note that in this particular case, the phase angle negative sigma t is pi over 4. So cosine of pi over 4 is the same as sine of pi over 4, which is 0.707. So we have 0.707 square here, which is positive, and we have the 0.707 here. Actually, we can also try to find out what is the maximum drag force and the maximum inertial force. We can do that by solving these two expressions separately. For the drag force expression, we know that it will be maximum when cosine term equals to 1. So essentially this part will give us the maximum drag force, which is 850 Newton. Whereas for the inertial force term, it will be maximum when the sine term here equals to 1. So this part gives us the maximum inertial force, which is 900 Newton. We can see here that the maximum drag and the maximum inertial are almost the same, where inertial is slightly higher than drag. Take note that we cannot just add these two values together to get the maximum total force, because whenever the drag is maximum, inertia will be 0. Whenever inertia is maximum, drag will be 0. But we do show that at somewhere here, when the phase term is equal to pi over 4, the total force is larger than the drag, as well as larger than the inertia. This does not, however, means that this is the maximum total force, but it's likely that the maximum total force will be quite close in this range, as we have seen previously in the profile of how the drag force, inertial force, and total force changes with the wave profile. We proceed to apply the equation for the total moment on the vertical pile. Again, we just substitute in all the values that we already found out. We remember that this part here and the cosine term here combined is the 425 that we get in the previous slide, and this part here and the sine term here is the 637, which we get on the previous slide. We have the D here, these two D water depth, the 8, and now the additional terms that we need to solve will be this bracket for the moment due to drag, and this bracket for the moment due to inertia. So we find out that the moment due to drag is this value, the moment due to inertia is this value, and the total moment is this value. So if we know the total moment is this value and the total force at this instant is this value from the previous slide, then we know that the total force at this moment is acting with a moment arm of 4.36 meter from the mud line. In this example, we have not specifically looked at wave breaking on the piles, and we only look at one single pile. We have not looked at a group of piles in close proximity. We will not cover this more advanced topic in this particular lecture.